And today we enter chapter 9 with some new concepts, more fun concept, give or take, okay, than just energy and power calculations. Uh, Chapter 9 is about center of mass and linear momentum. So far, whenever we have drawn a free body diagram, we have never actually we were never actually speaking about a particle, a dot. صح? We have always been talking about a human being, a box, a safe, a sled, a dog, a something. But for some reason, whenever we drew the free body diagram, we always drew it with just a dot. Why did we do that? Is it even okay to just draw it as a dot? ولا المسألة فوضى؟
It's okay.
Okay. Why is it okay? I have something as big as a human being. How is it okay that I am drawing him just as a dot?
Because there is something called center of mass.
Okay. So today we are going to look at this whole center of mass concept. Okay, and use it heavily. We'll define it, we'll work around with it, and then we'll do some fun stuff with it. And I'll show you some fun images about what happens if you muck up center of mass calculations. So, if I have a uniform square, it weighs exactly the same everywhere, where will its center of mass be? فوانا اقول سكشن 30 نشيطين ويتجاوبوا معي في اللكتشر. وينكم؟ ليش نمتوا؟ Are you here? Did I get disconnected? Okay, maybe my connection is not good enough.
We hear, Doctor.
Okay, there we go. You can hear me. That's always good. Okay, so the center of mass is going to be right at the center. Okay, fair enough. What about a 3D object? Again, it will be right at the center. No harm, no foul. That's okay, that's cool. But let's take more realistic objects. I have a ball. And now when I throw the ball in the air, okay, it has a trajectory, it moves in a certain way. If I throw a ball up at a certain angle, initial velocity at an angle, will I get a parabola like this, like our equations that we were using, v equals u plus at, s equals ut plus half, at squared, v squared equals u squared plus 2as? Will we get a parabola like these equations describe? With a real ball? Yes, no, maybe.
Yes.
Okay. Fair enough. Balls are usually symmetric, nice, spherical objects. Very nice. What if I instead throw something like a baseball bat, which is asymmetrically shaped, weird, quite big and long? One side is heavier than the other. What are we going to see if I try to throw that into the air? Okay, Lath says it will rotate. That is true. Now, as a big object, it's not going to simply go, as a nice parabola. It will have some rotation, it will have some weird movements. Let's see an actual video where that happens. Okay. So we're just throwing random objects in the air. Okay. Does that look nice and round? Does that look like nice and parabolic? Does it look not nice and messy? Okay.
Yes.
Let's put a bright orange dot on the center of mass and do it under dark light. Okay, under black light. Let's see what happens. Take a look. So, what did you notice? Did you notice anything at all? Let's play it at a slower speed and take a look. What do you see?
It's take a curved path.
It's taking a perfectly parabolic path. All that rotation and flailing around that we saw, when we're just looking at the center of mass, it disappears. It's as if it was never there. So although the rotation makes it look like this, okay, if I mark the center of mass, I have a perfectly parabolic shape. Okay. And this is what we have been doing all along. When we were, drawing a human being or a building as a simple dot, we were simply looking at its center of mass and saying, okay, pretty much this is the interesting bit. We'll apply all the physics to this bit. Okay? Now, if I have a ball, tiny ball, and I want to balance it on this triangle, it's really, really difficult, right? Where is the center of mass of this ball?
In the middle.
Exactly in the middle, which is why it makes it very, very difficult to balance this ball, because you need the center of mass to be perfectly aligned with the center of the triangle, so that your forces is literally mg and n cancel out and your thing doesn't move at all, not a bit. What happens if it's a tiny, tiny bit off? If it's even 0.1 millimeters off, what you will end up with is, you will end up with mg cosine and mg sine. And this mg sine is going to make it come down. Okay. A baseball bat, when I try to do the same thing, I also need to put it at the center of mass. But its center of mass is not in the middle. It's towards one end, the heavier end. So it will look like this. If I'm trying to balance a bird, the bird's center of mass is actually at its beak. And a human being, their center of mass is actually somewhere around their hip. Now, this is assuming, just a normal, healthy human being. If you are on the large side, like I am, or if you have a big head with a big brain, so your head is heavy, your center of mass is actually going to be different. Before looking at continuous large objects, let's consider just normal objects, just tiny systems of particles. Say I have two normal balls, symmetrical, spherical. Each one of them has their center of mass right in the middle. Now I want to find the center of mass for the entire system, for the two balls together. Where do I put it? اثنيناتهم مع بعض, where is their center of mass? Right in the middle. Okay. What if I make one of them slightly bigger? Where's the center of mass now?
Same.
Slightly toward the bigger one.
So we have one answer saying here, one is saying slightly to the side. We have someone in the chat says slightly to the right as well. So 1 for this, 2 for this. Anyone thinks it's going to the left or up or down?
On the right side.
Okay, we have one more person saying on the right. It is indeed going to the right side. It is going to the heavier side. Okay. So this is the correct answer. It goes towards the heavier object. Okay. How do I calculate it? Now, to the right, to the left, these were very unprecise terms. How much to the right? How much to the left? How do we calculate this? What we do is we choose a point which we call 0 point. Okay, in this case, for example, I have chosen my 0 point to be here. And I apply this formula. I take m1 multiplied by x1. Then I add m2 multiplied by the distance to the center of mass of the second object, x2. And then I divide it by the sum of all the masses, m1 plus m2. And the answer I get is x center of mass, which is measured from the 0 point. Okay. What if I have more than 2 balls? What if I have 10 balls, 20 balls? Then the general term is sum of mi xi over sum of all the mi's. So I take m1 x1 plus m2 x2 plus m3 x3 all the way to m20 x20, for example. And then I divide it by m1 plus m2 plus m3 plus m4 all the way to m20. Okay, I have a question for you. Here, I chose point 0 to be here. Can I instead choose the middle point to be 0.0, the middle point between the two balls. Can this point be 0?
Yes, we can. It can.
No problem, right? The only thing is,
Yeah.
when you are doing your calculation, x1 will be negative and x2 will be positive. So you need to be careful about that. Okay. Can I, for example, choose it on a totally different location? Say, for example, here.
Yes.
Yes? Anyone disagrees with this? Yes? No? Yes, we can put it there. We can put it at any place we choose. But can and good idea are two very different things. What will happen if I choose my 0 point over there? When I try to find x1, I will end up with this. When I try to find x2, I will end up with this. It will have an angle, theta 1 and theta 2, and I will have sine components and cosine components, or i's and j's and magnitudes and angles, which is generally bad idea, but can be done. Okay. If you're a masochist and you like pain and you want to do it, it's up to you. But generally, a good idea is to choose a 0 point, which makes your calculations easier, not more difficult. Okay. Choosing the blue option is basically like seeing John Cena or The Undertaker on the road and deciding that punching them is a good idea. I mean, can you punch them? Yes. Is it a good idea to punch them? Unless you are another wrestler, that's probably the answer to that is no. You don't want to punch them. Okay. Any questions so far?
No.
Let's do our first PIQ. You will find it under today's lecture. And since you still have to connect and all, let's give it about 2.5 minutes. Okay. I'll be back in 2.5 minutes to figure it out with you. Okay, how are we doing? Let's see, time's up. Pretty much. Okay. The vast majority of people have chosen option 4. Couple of people with each other option. It's very nice. It means the idea has gotten through. Indeed, the correct answer is it is closer to the sun than it is to either Earth or Mars. So the size of the sun, the mass of the sun is huge. Okay. The mass of the sun is really, really large. And compared to the size of Earth or mass of Earth and mass of Mars, it's nothing compared to the sun. So we said it's closer to the sun. Where do you think it is? I'll draw a few points and you tell me. So I will assume that the center of mass here. So I'll write 1, 2, 3, 4, 5, 6. Which one of these options do you think? Where is it?
2.
4, 2s, 4s. So pretty much everyone is between 2 or 4. Now, I haven't actually done the calculation, yeah, but I would imagine it to be somewhere between 1 and 2. Somewhere here, closer to 1 probably. This is how big the difference is. Do you want to do the calculation and see which one is it?
The sun is 300,000 times heavier than the Earth.
Yep. So it's probably going to be just barely out of 1. So I'm going to choose the center of mass to be right in the middle between the sun and the Earth. Sorry, I'm going to choose my 0 point to be right at the middle between these 2 points. So I need to do mass Earth x Earth plus mass sun x sun divided by mass Earth plus mass sun. Can anyone help me find these values very quickly? Don't want to take too much time. Mass of Earth, mass of sun, distance between sun and Earth centers. There we go. 1. So mass of sun is 1.989 x 30. Mass of Earth is Hayyallah Miskeen 5.97 x 24. And the distance between them are approximately 149,600,000.
150 million.
Sorry? 150 million, give or take.
Million.
Good enough. D equals 150 million kilometers. Okay. I'm going to keep it in kilometers. Can anyone do the calculation?
It's easier if we chose the 0 point to be on the Earth, maybe, or
On the Earth itself?
yes, because of the distance.
It introduced the complication that the distance of one of them is going to be 0, and that might make some calculations weird. So I'm just going to keep it as, 150 million divided by 2. And then I am going to store my answer. Okay. Okay, here we go. Ready? 1.989 x 30 times minus that distance. And then 5.97 x 24 times that distance. Then I am going to add them up, and I am going to divide it by 1.989 x 30 plus 5.97 x 24. Believe it or not, the answer I am getting for x sun compared to this 0 point is minus 74,999,549.8 kilometers. Bear in mind that the distance, okay, is equal to 75 million. So the correct answer turns out to be, it's almost 1. It's just, barely 40 kilometers away from the center of the sun. That's how much closer to the sun than the others. Okay? That was in 1 dimension. What if I have a 3-dimensional object? So instead of the sun and the Earth and Mars being in the same plane, it's 3-dimensional. كل واحد منهم في صوب. How do I find its RCOM? Now it's instead of X center of mass, now I have R center of mass. How do I find it? Hint, we do the same thing we have been doing for velocities when we have multiple dimensions.
We make the calculation in 3 components.
Exactly. We do the x-com alone, the y-com alone, and the z-com alone, and then each one of them is a component of a vector. Easy peasy. Okay. Let's do a checkpoint. Okay. If I have this uniform square plate, it's uniform, the mass is equally distributed, and I decide to remove square 1. So ignore this bit for now being. Okay. And I decide to remove square 1. Where will the center of mass of the plate be if we remove square 1? It's on PIQs. Okay, let's see. So the vast majority have chosen close to square 3, which is indeed the correct answer. So if you remove this, it is now heavier towards number 3. So just like when we have the two marble balls and it was closer to the heavy side, when we have the sun and the earth and it was closer to the heavier sun, now it's going to be closer to the heavier side. Okay, what if I remove both 1 and 2? Well, now the entire heaviness has gone to the bottom side equally. So it will be between 3 and 4 equally below the center. Okay, what if I decide to remove 1 and 3? Well, the weight here is equal to the weight here, and the weight here, the mass here, is equal to the mass here. So it is balanced in this direction and balanced in this direction. So the center of mass does not move, it stays in the center. What if I remove all 4 of them? Where's my center of mass then?
In the
At
middle.
the origin.
In the middle. It's balanced. It's perfectly balanced. Another way to think of, a very quick and dirty way to think of the center of mass is to think this way. Okay, if this thing is not perfectly symmetrical and I put my finger right here in the middle of it, which side is it going to tilt? Which side is going to be heavier? My center of mass is towards that direction. Now, we have an interesting problem here. And I actually want you to do it in groups because it's quite an interesting problem. So I'm going to split you into groups. Go to question. This one, go. I'll split you into, we'll use the breakout rooms feature. Set up breakout rooms. Good. Good. Okay. And I'll give you 4.5 minutes. Okay. To discuss. Actually, you know what? Make it 5 minutes to discuss this. Let's see how well or unwell this goes. I look forward to it. Okay, we are back. And I'll give it a couple of seconds until everyone else joins back. Okay, so I am extremely happy to see that a really, really big proportion of students have gotten the correct answer. I mean, we are talking about 71 students out of 90 something, which, no, 74 out of 91. So we're saying about 80% of students got this correctly, which is a really good job. Well done, guys. Okay. Job very well done. So what we do is we say, okay, this is length L and this is length L. Center of mass of this will be here. Center of mass of this will be here. So this is L over 2, 0, and this is 0 L over 2, the position. This is, they have the same mass. So I do, okay, x-axis alone, just like we trained, just like we said, we do each axis alone. So x center of mass would be ml over 2 plus m0 over 2m, which the m's cancel out and you end up with L over 4. Y center of mass, you have 0 for this one, but L over 2 for this one. So you have m L over 2 over m plus m. And this is also equal to L over 4. So our final answer will be L over 4. L over 4, L over 4. So our mass will be, center of mass is going to be closer to somewhere around here. Which makes sense. I mean, if you imagine, I am going to complete the square like this. Okay. If I had a complete square, where would the center of mass be? It would be right here in the center.
In the middle.
So if I take half of it off, it's going to go to the quarter. Just like we did. So this is basically the equivalent of this case. Okay. All right. This is really nice. Now we have a sample problem in the book, which is quite a doozy. So we should do it. Sample problem 9.02. But so the question says, figure 9-4a shows a uniform metal plate of radius 2r, from which we eat away a disk of radius r. The disk is shown in figure 9-4b. Using the xy coordinate system shown, locate the center of mass comp of the remaining plate. So we have this plate, circle, We take away this circle and we have this remaining. What is the center of mass of this? Now, what we do know is that the center of mass will go to the right. Since we ate from the left, الصوب اليمين صار أثقل, it will go to the right. The only question is how much to the right? Okay, and how do we calculate it? We don't have any numbers here, so it's just letters. Fine, fair enough. Let's do it together. A lot of people indicated in the reading check that, this was a big problem for them, this sample problem, so let's do it. But before we do it, I'm guessing some of you are bored. Can any of you think of a real-world application of center of mass when it's a problem, if we don't do it right?
Demolishing buildings.
That would be a big problem, yeah. You do it incorrectly and it will fall on your head on the wrong side. Any others?
Cutting a tree down.
Sorry?
Cutting down a tree.
Cutting down a tree, also a very good example. You do not want it to fall on your head. I'll show you something that you might have never thought about before.
Riding a snake.
Sorry, say that again?
Riding bicycle.
Yes,
Waiting.
that is very important. And I have never managed to figure it out, which is why I don't know how to ride a bike. I accept free lessons if anyone wants to give me one. But let me show you. Okay. Here's an airplane. Okay, very, very quickly. Okay. You have fuel, you have engines, you have the wings, you have a cargo, you have bags, you have people in it, you have all sorts of things in it. Yeah. Which means that a center of mass for the plane, okay, can be calculated. Now, what happens if we don't calculate it correctly? Well, you end up with this. This is not a computer image. This is not a CGI. This is a real photo of an airplane which has fallen down on its behind. Okay. So what these people probably did is they put too much cargo to the back of the plane without enough supporting on the front. And just like a seesaw on the playground, the plane decided to tilt. Needless to say, this is probably not how you want your plane to go. Okay. If you've ever traveled on a very full flight, when every single seat on the airplane is taken, you would notice the air crew telling you stuff that makes no sense, to you at least. Things like, please stay seated, there are enough people at the toilet, wait until they sit down, then go. We serve food one row at a time, section by section. لما الطيارة توصل أنا أول واحد مسوي تشيك إن لكن شنطتي ما جالسة تطلع، أو أنا آخر واحد مسوي تشيك إن المفروض شنطتي تطلع أول شيء على أساس إنها آخر شنطة داخل الطيارة but I'm still waiting. Or when you're boarding the plane, okay, or even when you're disembarking the plane, they tell you, wait, don't all stand up at the same time, wait شوية شوية. Now, to us, this is just a pain because, تعبنا صارنا 18 ساعات في الطيارة, we want to get out of here. But the reason they tell you is so something like this doesn't happen. And there was an accident, okay? There was an accident, and it's considered one of the weirdest accidents in aviation in modern history. في طيران صغير كان يستخدم طيارة صغيرة مثل هذه في إفريقيا. I think it was 2006 or something like this, 2004, 2006. And what happened is the pilot was preparing the plane for landing, And as usual, as soon as the pilot says, okay, تم الآن تشغيل إشارة ربط الأحزمة، يرجى العودة إلى مقاعدكم, everyone suddenly wants to go to the toilet. Yeah? Nobody wants to go to the toilet until it's time to land, and then everyone suddenly has the urge. And the pilot told air traffic control he was about to land, and suddenly the airplane went nose down, dipped so badly, and ended up crashing. Everyone on that airplane died except for one person. بعد تحقيقات جرت سنة كاملة تقريبا, they finally figured out what the problem was. Turns out, on the small plane, about 12-15 people decided to go to the toilet at the exact same time, got up and ran towards the toilet عشان سريع سريع قبل الهبوط, which caused a shift in the center of mass of the plane to the front. Very quick. The pilot couldn't control it in time because it was very, very quick, and that caused the plane to just crash. Bad accident caused by center of gravity. Anywho, back to the sample
Doctor?
problem. Yeah?
I don't know, have you ever seen with videos of guys drifting their cars and they're driving in two wheels? Is that
Yeah.
also a concept behind the center of gravity?
Yes, exactly. Now, most people who do it don't know the physics of why this actually works. They just think they're magicians, but that is exactly the reason why it works. Okay, so you will notice something. For example, when they're driving on two wheels, pretty much in every single video of these, عندك شخص أو شخصين مطالعين من الدريشة ومطلعين جسمهم نصه من الدريشة، صح ولا غلط؟
صح.
إنزين، ولما يكونوا طالعين نصهم من الدريشة يكون جسمهم بالعادة مايل على أي اتجاه؟
تحت.
تحت، صح؟ على صوب التواير.
Yeah.
So what they're doing is, here you go. This is the car on its side, okay, and هم مطلعين نص جسمهم برا, 2 people at least, okay, and they are putting extra mg cosine theta to this side, to the side of the wheels, to support إنه السيارة جاية على جنب. So, and that way, the center of mass, center of gravity, center of mass, stays around here somewhere, and the car doesn't flip. Yeah? So, we have the circle, radius 2r. We decide we're going to remove a small circle of radius r from it, and want to know where is the center of mass of the remaining part. Well, what we do know, okay, أنه أصلاً it was in the center, and now it's going to be probably somewhere here to the right. We just don't know where exactly to the right. Yeah? Okay. I'm going to draw the 3 of them. Small circle, big circle, partial circle. SCP. Okay. Center of mass for the small circle is exactly in the center. Center of mass of the big circle, exactly in the center. For this, towards the right, we don't know where. Let me draw them فوق بعض. Okay. Let me draw a few things. Okay. Now, the location of the center of mass of the big circle is right at the center. The location of the center of mass of the small circle is to the left at minus r, because it's the center of the small circle, so minus r, since this is radius r. So far, so good?
Yes.
Yeah.
Okay. Mass of circle is equal to mass of small circle plus mass of partial circle. Also, so far, so good?
Yes.
Okay. Let's do the calculation. X center of mass. We have x-axis, we have y-axis. Let's do x center of mass first. ms xs plus mp xp over ms plus mp. And that is the x center of mass of the full circle. صح? If we take this circle, center of mass مال واحد فيهم هنا والثاني somewhere here، فلما نجمعهم مع بعض بيجي في الوسط صح؟ at 0.
Yes.
اوكي. خلينا نعوض. xc 0 xs minus r xp ما نعرف ايش ms mp نعرف شنو يساوي mc. بالتالي وصلنا هنا. We have a formula for us. xp equals minus xs ms over mp. تو عندنا مشكلة. We don't have a mass. How can we figure it out? Any ideas?
MS is quarter the mass of MP.
ms is quarter the mass of mp or mc?
MC.
Why? Can you explain to me? It might be right, but can you explain to me why did you decide it's exactly a quarter?
Because of the radius, I think.
Okay, fair enough, fair enough. I think I know what you're doing. Mass equals density times volume. Volume is thickness times area. Now, mass of S and mass of P, الدنسيتي مالهم نفس الشيء. هم نفس الدويرة أصلا، من نفس المعدن. density نفسه، thickness نفسه، اللي يختلف هو فقط الاريا. بالتالي هذا واحد هذا واحد. area S over area P. area S على area C minus area S اللي هي area P. نقدر الحين نحطه. Turns out ms over mp, the small circle, is a third of the mass of the remaining of the circle. Not 25%, but close enough. So xp is 1/3 r. So it's going to be here, and this distance is going to be r over 3. واضح? Any questions on this?
That's clear.
Okay, that's good. Now, in 3 dimensions, we said instead of xcom, we'll end up with rcom, where we have 3 components, x, y, and z, or I, j, and k. Fair enough. Now, if I simply just bring this up to here, okay, I want to make it look nicer. I end up with this MRCOM يساوي MR1 plus M2R2 plus M3R3 إلى آخره. What happens if I differentiate this with respect to time؟ وأطلع كل شيء يتحول إلى velocity صح؟ MVCOM يساوي M1 V1 M2 V2 M3 V3 بدل كان MR صار MV. أنا ما غيرت شيء I just differentiated صح؟ Do you
Yes.
see where am I going with this? What happens if I differentiate it again?
Acceleration.
Okay. So I end up with this. And what does this look like?
Force.
Force. MA center of mass يساوي force 1 plus force 2 plus force 3 which is what we have been doing من أيام chapter 4 صح؟ This is what we have been doing. نحن جالسين ايش جالسين نسوي؟ ناخذ الفورس على كل القطع الصغيرة ونقسمه على التوتال ماس ونطلع الاكسلريشن صح ولا غلط؟ This is what we have been doing. So we have just proven from first principles انه نحن اللي من البدايه كنا جالسين نحط نقطه حال big bodies ما كنا جالسين نخربط. We were just simply doing what physics wants us to do anyway. It wasn't an approximation. So we're not doing مثل المدرسة انه اوكي نحن هذا ما صح لكن نحن جالسين نسويه وبعدين بنعدله في المستقبل. No. We're doing everything correctly. Let's do one more PIQ. A system is made of ball A of mass m moving to the right at speed 2v and ball B of mass 3m moving to the left at speed v. Before the two balls collide, what is the magnitude and direction of the velocity of the center of mass of this system? So we know what's the velocity مال A وحده والvelocity مال B وحده. بس الcenter of mass مال السيستم وين جالس يروح؟ I'll give you about 3 minutes to do the calculation. That should leave us about another 3 minutes to go over it ourselves. Okay, let's see how we're doing. So we have 62 people who chose A, few people who chose other options. Let's see. Ball A, ball B. Ball A going to the right 2V, ball B going to the left V. M and 3M. سماعتي مفتوحة صح؟ I'm not talking to myself. Yep, okay. We want to know the velocity of the center of mass. Just like we did for XCOM, we do for VCOM. بس وين ما كان مكتوب X نحط V. M1 V1 plus M2 V2 plus over M1 plus M2. طيب. I'm taking the center to be between them, somewhere in the middle. So M2V minus, لأنه it's in the opposite direction, minus M3V over M plus 3M. We get minus V over 4, which means V over 4 to the left, which means this is indeed correct. And I'm really, really happy with the answers we're getting. Now, I don't know if you are a really good bunch or what's happening, but I have never had so many high percentages of correct answers in PIQs before. So I'm really, really hoping this means that the point is getting across. Sincerely hoping that, which means I'm doing my job. Or that, Ahmed Awad is doing his job. Either way, I'm happy. Do we have time? It's 1:18. لا خليها حال المرة الجاية. It will be too quick. Okay, so that's all for today. We'll stop here. And inshallah, on Monday, we will continue with 9.2 to 9.3 and maybe a bit more to 9.4 and 5 if time allows, depending on how fast we go. Okay.